Excellent. So I'll talk today about large image datasets and their state. And this is joint work with Amir Alush, who is my collaborator, and also with Professor Carlos Genspring from Stanford, who is also our third collaborator and was also my postdoc advisor at Carnegie Mellon. So when we look around us, we see that images and videos are becoming super popular, and there are huge amounts of data around us, starting from billions of surveillance cameras, social networks, manufacturing, and also autonomous vehicles are generating huge amount of visual information. From my personal experience, I spent the last 5 years at a fruit company, and I was heading a 10-person computer vision team, and we were working on manufacturing, and we got millions of images a day, but we found out that most of our time was wasted on shuffling data around, dealing with different formats, dealing with wrong labels, dealing with corrupted images and transformations, and relatively small amount of the day-to-day work was actually the fun stuff of algorithms. And this got me a little thinking about whether it was my personal deficiency or is it across all other companies that are working with computer vision. So I left Apple around a year ago. And since then, I'm looking at the computer vision market to see what are the interesting use cases that are emerging and what are the challenges. So I took the year to talk to many companies and seen a lot of cool use cases that I was never subject to them before. So for example, Scott is a company from New Zealand who is doing a robotic butcher, which is a use case I never heard about. Software is a company from east of the US where they sew t-shirts. And I wasn't aware of that either, but most of the t-shirt production in the world is manual. So it's pretty complicated to do it fully automated. Hover is a company doing 3D reconstructions of home. And we know is a London-based company which looks into trash bins and finds and does food waste reports for restaurants. So across the board, we see a lot of interesting type of applications emerging. And we've taken the time to interview many of them in order to see what are the pain points and what are the commonly used tools and what are the missing tools. And the majority of the companies, so it's been spread across all verticals, but mainly we talked with manufacturing, retail, self-driving, and so on, although there are many other applications in different domains. So I want to briefly go over some of the interesting findings we found by trying to investigate what's wrong with the current computer vision infrastructure. And one of the interesting questions is whether companies are working with videos or images. So we found out that about 90% of the companies are working with images. Maybe 10% out of them are having video sequences, but they split it into frames. And working directly with videos is not so common across companies due to the complexity and the size of the data sets. A lot of the companies we talk to are working on supervised approach. So most of the companies are doing labeling and then training supervised models. Unsupervised is pretty rare. And most of the companies, maybe 60–70% are using the cloud. So a very common use case is storing files on S3. And a lot of the companies agree that when they do data iterations, which means maintaining data, looking at the data, debugging data, visualizing data, this is the bulk of the work, and the algorithmic and deployment and the rest is a relatively low aspect of the work. So in terms of the common pain points, we see that a lot of the pain points are around data. especially how to store and manage the data, find where are things, find interesting subsets for training, and dealing with annotations, issues with annotation, bad annotation, trying to understand what's going on, and also versioning, or what we call lineage, which is trying to find differences between image that was yesterday, there was a small change, and now the image today, and it's really hard, and there are multiple people working on the data set, it's really hard to understand who did what, and what was before, and which version of the data set was used for the training. So those are kind of the most common pain points we see across many computer vision companies. And if we summarize, the majority of issues are around data quality, especially fragmentations, which we see that companies have no clue where is their data. One funny anecdote, we talked to a Fortune 500 CTO that said that he has no clue where the data is somewhere in S3. So many companies really, it's really fragmented. It's found in different places, different formats, different teams cannot share data. And over and over again, companies are writing their own tools in order to deal with issues with data. I can give one example. For example, companies are tending to work with S3, but when they want to copy images to view what's inside, there is no preview in S3. So this is very frequent that companies are copying files, looking at the image, seeing, oh, this is the wrong image, they copy more image locally, and it's really hard. So part of our work, we build tools to do a preview for images on S3, but it's really not efficient that each and every company builds those tools on their own. It would have been much beneficial to have all the tooling ready-made, especially those building blocks that are really essential. So this is not just a problem for computer vision teams, it also slows down companies in general that are performing computer vision in production, and the quality of models is affected, and a lot of time and money is wasted, especially that computer vision teams like to do the algorithmic side, like to do the deep learning modeling, and they pretty much hate to do work around data and data issues, and that's they typically avoid it and give it to some juniors or interns or whatever. And I want to give one example in a bit more detail about a very popular data set, which is ImageNet. It's one of the most cited data sets in computer vision with 32,000 citations. And ImageNet is a data set which is it's treated as much as a state-of-the-art academic data set, was done by professors, but we think it kind of shows all the problems that are really evident in computer vision today. So let's start in discussing some of the issues that we investigated the ImageNet in order to highlight some of the issues that we're talking about. So one interesting thing that was not really already known is that there are a lot of broken images that are images that are try to download from the web, some let's say e-commerce website with some labels, and they were downloaded, but they're actually broken and they have valid labels. So this is anecdotally, I don't think it was ever found, but we found out that there are something like 200,000 images like that out of 13 million. So it's a huge amount of information. And if we illustrate what's the problem with this kind of labels, is you can see here, there are all kinds of white images that have no content, but they have all kinds of actual labels like scanner and Fairfield or snatch lock or stabling and lederhosen, whatever it means. And those are labels that are just confuse the model because they seem to be valid labels, but they're actually, they make no sense. And those images should be removed, otherwise the model quality suffers. And the reason it's was not really found before is that because the dataset is so big and computing on it is painful, that people typically just ignore the issues and just assume it will be okay and the network will we learn from the data because it's big enough, but that's a real issue. Another interesting thing we found about ImageNet is that there are almost 2 million duplicates out of 13 million datasets. So it's more than 10% of the data is duplicates. And this is a problem because first it wasted storage, it wastes compute, but it's even worse when there is a train test split. And then we found out, and this is some dataset that was derived out of ImageNet. It's a cleaner dataset from Alibaba, where we see that there were around 100,000 train test leaks, which is a real pain because we think the model is general enough, but actually the model may memorize a lot of the training images and then be very good at the test. So that's an issue. Another interesting thing we found in ImageNet, which I'm not sure was discovered before, is the population of bad labels of even the same image. So in this example, we see same image of red wine glasses, but human annotators gave it a lot of different titles. And again, the model cannot make sense about which is the correct class. So those images should be most likely removed. Otherwise, it doesn't make sense. Another thing we found about ImageNet, which I also don't think it was pre-known, is that there is a lot of things related to agriculture, to plants, especially fern issues. We found out there are tens of thousands of fern images that were fed into the dataset. You see, everything is the same image, but they have so many technical Latin terms that describe different ferns. And of course, it doesn't make sense. And most likely the human labels that went over the data had no clue what it means. And that's why those issues were never found before. Another thing we looked at is the occurrence of bad labels. And everything we did, and I'll soon describe, is using unsupervised approach. So let's look at some images. For example, this is an egg from ImageNet, but it was labeled the secretary. So it's pretty funny, and it's probably either annotators, they don't know English, or maybe they're joking, or maybe it's a mistake and so on. But all of those issues come up very frequently. And the thing is, we don't want to find bad labels one by one, because this is a waste of our resources. And we want to automate finding and identifying those bad labels. And the way we did it is by grouping similar images together. So all the eggs are very similar, but if there is a population of egg labels, which is very frequent, it makes sense. But if there are a label secretary around the cloud of egg labels, it's most likely a mistake. And this is how we found those weird labels. In addition, we were also able to identify funny type of labels, which is things like this dog, which has a cap on his head and the label is cap, or this sheep riding a motorcycle, which is domestic sheep. So that's a pretty funny label. And those are the things we can also find automatically. So overall, once we understand there is an issue and there is a problem, and there are a lot of data sets which are super noisy and they are slowing down research, we started to write a free tool, which is named FastDup, that we wanted to share with the community. And it's available on our GitHub repo. And the design goals around FastDup are the following principles. So first, it has super easy to use. So it's a Python package. You just do pip install FastDup and you're done. It's also super efficient in terms of we put a lot of energy into the C++ implementation under the hood. And for example, the full ImageNet by Alibaba, the cleaner version, which is 11.5 million images, we're able to process it in around $1 cost on spot instance on EC2, even without GPU. So that's really way cheaper than could be been available before. And it's accurate in the sense that we can scale to multiple types of verticals and data sets from different domains, but still it works pretty well. The model is very general, and that's why it's becoming more and more popular. And of course, it is a free tool. So some examples about the functionality we added to FastDup. We started with the duplicate detection that I've shown earlier, but also we added outliers. So outliers are in the context of the actual dataset. So this is a dataset IMDb, which is a face recognition dataset. So we should expect everything to be a face. But we've seen here that there are radios and shoes and ocean. Again, we automatically identify it without regard of the labels, just by the content of the image. And this is very valuable because these images should be removed. Other types of functionality that are readily available in FastDup are automatically identifying corrupted data, bad labels, and clustering and search. I will talk in a bit more detail. So FastDup was released 3.5 months ago, and we crossed the 80,000 installations, which is pretty cool. And we start to see more and more applications. One example is Kaggle users that start to use FastDup for different type of domains. So it works really well on both butterfly, tires, strokes, germs, cardboards, and all kinds of other information. So we are really proud to see this activity, and we would love to encourage as many users as to try it out. One of the things we added to FastDup, and this is not readily available in other projects that we're aware of, we added also the ability to do graph analytics. And the reason is that we want to semantically understand the data. So, for example, this is data taken from a food data set, food 101,000 images, and those are all the MAME images. But if we have some kind of nearest neighbor model where we query this image and we get the most similar image is that, and we query that image and the most similar is that, and we query and so on. So this is a multi-hop journey that is super complicated to process. And what we did in order to simplify our life is actually cluster those things together. And then you can find clusters of activities of different domains, and everything is unsupervised without relating to the label, which is very cool and help us understand the dataset much better. And this also help us do semantic aggregation. So everything here is again taken from ImageNet. It's a 13 million image dataset. It's really hard to understand what's inside, but once we have the semantic capabilities of understanding what's an apple, we can actually build clusters of different type of apples. We can look at the labels, and we can understand what's going on. So you can see, for example, a mild transformation like shrinking the apple and some color balances and so on. We treat them really well. We can cope with them. And our goal is to allow, instead of fixing a single label, we can fix thousands of labels together, and by building this hierarchy of understanding better our data set. The one last thing I want to discuss about additional functionality of FastDup is the ability to do graph analytics. And this is, again, ImageNet dataset. What we did here, we built a nearest neighbor model to understand what are similar images to each other. And we start from a random image. And this is real random. I did it a few times, and each time I got crazy presentations that are super cool, in my opinion, but I wasn't expecting anything like that. So what happened is that we started from a random seed, which was this wheel cart, and then we let FastDup find the most similar image on this 13 million data set is this wheel cart, and so on. And then here we progress to the right until we see bicycle wheels, and then we see this funny bicycle, which is a transition between bicycle and this kind of old-fashioned bicycle. And then we get to modern bicycles, and then to scooters, and then to motorcycles. And everything is learned from the data itself without regard of the actual labels. So this is some of the functionalities of FastDup. I would love everyone, especially in this session, to try it out. And as I mentioned, it's free. And I want to show, or at least to try and show, some of the functionality we have in a Jupyter. So I did prepare one Jupyter ahead, but I hope it will work. As you know, it's we are on on a live show, so I hope everything will work. So this is an example of how you can run FastDup on the food dataset. So it's a cool dataset. The first thing you do, you just pip install FastDup, and then you import FastDup. And next thing I'm doing, I'm downloading the Food 101 dataset, which is about 4.65 gigabyte dataset. Next, I'm running FastDup. So the API is pretty simple. What I do here, I run the actual folder of the dataset, and then I give an output folder, and the rest are some configuration parameters. So it runs on those subset of 10,000 images, and it takes a few minutes. And this is on a Colab notebook, which is not so powerful. So you can speed up with adding more cores, it will run faster. And this is just a single run. So I run it only once, but after I run it once, it generates the results into the outlook there. And so we do only a single pass on all the images. We don't iterate on the images anymore, besides of this run. And the next thing we can do a lot of slicing and dicing on our datasets in different aspects that I'll show next. So first thing I can do is create a duplicates gallery, which is finding duplicates from the analyzed dataset, and then we show them. So you can see while it's supposed to be a clean dataset, there are a lot of duplicates, and of course, those duplicates can be removed, and we have means also for removing them automatically. The second type of functionality I want to show is outliers. So this is, again, without regard to the labels of the dataset, we just look at the content of the images, and you can see here, we have a black image, we have a keyboard, we have, I don't know what it is, we have Batman, and all those things are not food. And those are learned automatically that those are not food, and most likely they should be discarded from the dataset we train. Next functionality that we have is the ability to look at statistics. Again, with a single pass, we learn the image statistics, and then we can find out what are the most dark images, bright images, a number of colors, and so on, and all type of different types of statistics. So here I can show the most darkest images in the dataset, and this is where we are in the darkest region. We can look at the aspect ratio of the dataset, and here we get to the graph analytics. So one of the most interesting things to do is to create the component illustration. So you can see I've given a threshold which is pretty relaxed, so it doesn't have to be accurate, but you can see in this food dataset, there is a cluster of binets, or however you say it, which is looks like a tasty cake. And those are learned from the data without relating to the labels, but we just print the labels as a sanity check. And here also this bibimbap was cluster and so on, based on the content of the image. One last thing I want to show is that we added also support for TensorBoard integration. So you just export the data to TensorBoard, and then you can play with different types of layouts. So I can do a t-SNE, a two-dimensional t-SNE, and then I can see the different type of images are organized based on the feature vectors FastDup computed. And again, we don't have to touch the images. Everything was computed only once. We can do cool coloring, for example, to color by the different labels to see how they align in the space. We can click an image and find the most similar images in the dataset. Whoop. Yeah, maybe I need to remove coloring for that. Yeah, sorry. Something gone wrong. And we can also do label search. No, I think something is messed up in my demo. Never mind. So this is the tool we released. and I will let Talia ask if there are any questions. I would love to answer.
Awesome. Thank you so much, Danny. That was great. Of course, if you guys have any questions, please find the Q&A icon at the bottom. Ask them there, and Danny will be happy to answer them. So I see we have one right now. And okay, Danny, can you access it?
Yeah, I can rephrase the question.
Okay.
So I got a question from Guys Al-Masri. I hope I say it correctly. Hello, Danny, from your experience, are you able to train a model on a certain set of classes? Suppose every class has 1,500 images, which is a minimum. Of those 1,500 images, how many images you take of the same class in the same place? So I want to clarify something. We are dealing with the data before it's actually annotated. So we can choose the most interesting data for annotation, but we didn't do any model training, which is supervised. So everything I've shown so far is unsupervised, completely unsupervised. So that's why we don't need a specific number of images. We can learn, even if there are 10 images, we can learn the normal behavior and find outliers. But of course, it gets more interesting when the data is bigger. And we did get to the scale of around 10 million images, and we are also working on even further. So we are looking at 100 million images scale now. Very cool. Okay, so I see this is the, yeah, so no worries. So I see this is the first and last question, and we are also running out of time. So thanks everyone for joining, and I would love to interact in our Slack channel, try FastDup, and we love to hear any comments. Yeah, I have one more question. Let's do it. From Ahmed Abdullah. The question is, hi, Danny, thanks for the great presentation. FastDup looks very interesting. Is it only useful in the context of classification, or can it help sanitize detection dataset? Yeah, so we have some samples on our website also for object detection cases. What we did there, we first did an iteration of cropping the images based on the labeled objects, and then we cluster the labeled objects and we find issues where there are wrong labels. So that's the current use case we have in mind. But we would love to interact, and if you have any other needs, we would love to explore and see how we can add them to help you on your needs. Very cool. Yeah, so maybe I'll show, I have a question about where is our Slack channel. So I'll share again my screen. So this is our GitHub. Look for FastDup at GitLab, and then you have at GitHub, sorry. And then you have this link of Slack here. So you can just copy, and I'll share it on the chat. Excellent. So thanks everyone for taking the time, and it was my pleasure. Thank you.